Okay, continuing on with our Laplace transform playlist. Today we have another differential equation, and this one's a second order homogeneous differential equation. We have y double prime plus 10y prime plus 25y equals 0. And we have these initial conditions, y at 0 equals 1, and y prime at 0 equals 0. Okay, to get started with this, we're going to do just the same thing we did in previous videos when we did differential equations, and that's going to be, we're just going to want to take the Laplace transform on both sides of the equation. So on the left side, I can split this up on the addition sign, so I can break it out like this. We can write it as Laplace y second derivative double prime plus, I can factor a 10 out here and write this as 10 times the Laplace transform of y prime. And then again, factoring 25 in front, we can write this as the Laplace transform of y. Now on the right side, the Laplace transform is 0, it's just 0, and you can think about if you were to plug this into the definition of the Laplace transform, it's an integral. You zero out the whole integral and you just get 0. And then for everything we have here, we have definitions that we proved, we have formulas that we proved in previous videos for the first derivative and second derivative. So we'll use each of these. Let's just remember our definition for big Y of S. This is going to be the same thing as just the Laplace transform of Y. And so we can take this one here and put it in this form. Okay, so for our first term, the Laplace transform of the second derivative, we have this formula here. So we'll use S squared, big Y of S minus S. Y at 0, we already have that value, that's just 1. So I'm just going to leave that off. So we'll just have an S there. And then minus the second derivative at 0. Sorry, the first derivative at 0, and that's just going to be 0. So that's going to go away. Then for this next one, we're going to have 10 times, we'll use this formula for the Laplace of Y prime. So this is going to give me S big Y of S, and then we'll distribute in the 10, but our Y of 0 is just 1, so it's going to give me a minus 10 right here. And then for this last piece, it's going to be just 25 big Y of S. And this is all going to be equal to 0. Now what we're trying to do here is we just want to solve for Y without any derivatives. In differential equations, you can't always get an explicit answer in terms of Y, but in this case we can. So we're just going to focus on our goal on solving for Y. And so what we can do to get closer to that is if we get this, then we can get this where we can reverse this with an inverse Laplace transform and isolate Y. So for now, we just want to isolate this thing, which is this. We want to isolate these terms. So what I can do is factor out our big Y term to isolate it. We'll have S squared plus 10S plus 25. And then everything else I'm going to do is bring it onto the right side of the equation. So I'll add an S and I'll add a 10, and we'll have S plus 10 here. Then one quick note on this thing, this is actually the same thing as our coefficients on our original problem. It always works out this way. This is the characteristic equation, and so you're always going to get that same pattern. So what we'll do here is we'll just divide this on both sides to isolate this. So we'll divide by S squared plus 10S plus 25 and do it over here. Then this here will cancel out. And then one other thing I can do here is I can rewrite this, but now this here is a perfect square. So this can actually be written as S plus 5 all squared. But now, like I mentioned before, I can just reverse this with the inverse. I can take the inverse on both sides, because this is the Laplace transform of Y. So when I do that, this whole thing here is just going to be Y. And so we'll do it on this side as well. And so now all we need to do to get our solution is we just need to do an inverse Laplace transform. Now this thing, the interesting thing here is this thing is not quite like anything in our table. Okay, so I think we need to do some manipulation on it. Now one thing I can do, what if I split this up? So if I create this, if I write my 10 as 5 plus 5, then we're going to get cancellation. But I also, because we have a plus sign, I can split this into 2 Laplace transforms, or 2 inverse Laplace transforms. So let's see how this looks if I write this. We'll have S plus 5 and S plus 5 squared here. And then on this second one, we're breaking out this term. I'm actually going to bring the 5 outside of the inverse. We'll write it like this. And then we'll just have a 1. That's a terrible bracket. Okay, then we'll just have a 1 in the numerator here, and this we're going to still have our S plus 5 squared. But then we can cancel this with one of these, so we just have 1 over S plus 5 here. But now for each of these inverse Laplace transforms, we have formulas that can help us with this. Let me just create a little space for this. Okay, so let's start with the inverse of 1 over S plus 5, and for that we can use this first formula. If in this first one, if we just set A equal to minus 5, then we get 1 over S minus 5 is 1 over S plus 5. So putting minus 5 back in here, this first term is just going to be E minus 5t. Now for the second one, it's just a little more complicated. We'll need two formulas for this. Just notice that the Laplace of t is 1 over s squared. Now it's very similar to this if we think of this as a shifted function. So if we take Laplace of t, if we think of this like our f of s, and then if we shifted it by minus a, the same, we can use minus 5 again on this. So what I'm saying is if we just look at the Laplace of e minus 5t times t, what that's going to do is that's going to return this, but shifted by minus a, or s plus 5. So it's going to give us 1 over s plus 5 squared. So this piece right here is going to be this. So we're going to have our plus 5 e minus 5t times t, and that's it. So there you have it, second order differential equation with Laplace transforms. Thanks everyone for watching today. Have a good day.